Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds, space expanded exponentially, growing much larger in size. After this period, space continued to expand but at a much slower rate, and eventually we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. However, for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. Rather, they say that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang but a bounce, a moment when a shrinking universe reversed course and began to grow. According to their theory, the universe could bounce again. Today's expansion could be followed by collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be infinite. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. But what is noteworthy here is this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing, adding a bit of tension. The James Webb Telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise a question. If the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce or something else entirely? Join us as we dig deep into one of the thorniest topics in physics. The idea that the universe had a beginning or a day without a yesterday, as it was originally known, goes all the way back to George Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that described our early universe. Although many lepers and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is outdated. The Big Bang now is not the birth of time and space. We know that today in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff instead. Our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. No particles, no photons, just empty space itself. That empty space had a huge amount of energy in it, with the exact amount of energy slightly fluctuating over time by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new small-scale fluctuations are created atop them. This superposition of fluctuations of small scales or top intermediate scales or top large scales or top superhorizon scales is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on, but inflation will come to an end randomly and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a humanized hamster ball but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of 33 seconds or so, a brief amount of time but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise from just a few degrees above absolute zero to perhaps around 20 Kelvin or so over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive, it doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats and the hot Big Bang starts. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time collapses, that distance doubles yet again and again and again. The process is relentless. But once the Big Bang begins, all of that changes, as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within spacetime dominating its volume. These regions where hot Big Bangs occur will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early era. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem, it has sometimes been called a crisis for cosmology. Third, the 2 hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense since we believe that the universe should have started out uniform on average. And lastly, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby Cepheid stars. Taken together, these anomalies mean we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called quanta. These quanta come together to form the fabric of space and time. In this model of the universe, there is the smallest size of space itself, the Planck scale, or 10 to the power of -35 meters. Nothing, not even space itself, can be smaller than this. This means that the Big Bang couldn't exist in a universe with loop quantum cosmology. The universe could never get down to an infinitely small, infinitely dense point. When the universe was very small, really weird things happen mathematically. Infinities start to arise and threaten to tear the fabric of spacetime itself. It's at these locations where loop quantum gravity can come in to provide corrections to the physics we already know. Dr. Ushtaker at Penn State University, who led a study showing that the universe started in a bounce rather than a bang, said, "At such places, one has to use quantum geometry underlying loop quantum gravity. The quantum-corrected equations predict that there is an effective repulsive force. This means in these regions, when the universe is very small, the repulsion would result in a bounce. If our universe originated in a bounce, that means there was another universe before us. That universe went through its life, perhaps expanding and eventually contracting. Once again, as all of the matter and space-time of this universe came together, it ended in a spectacular fireball. Then, in a giant bounce, our universe was born, like a phoenix rising from the ashes of the old universe. This isn't an entirely new idea. Physicists have tossed around the idea of the Big Bounce for several decades. Even farther back, cyclic time is present in Hindu cosmology. If loop quantum cosmology is the correct model of the universe in its infancy, the universe would have had very high curvature. To visualize this, think of a globe with positive curvature, a sheet of paper with flat curvature, and a saddle with negative curvature. Evidence of this would show up in the cosmic microwave background. When you look at the cosmic microwave background, you realize that it is not uniform. There are small differences in temperature from one point in the sky to another. If you plot these temperature differences as a function of scale, you get one of the most powerful tools of cosmology: the angular power spectrum. Evidence of the curvature of the early universe would show up in the angular power spectrum of the cosmic microwave background. Some of these effects would show up at extremely large scales, larger than the size of the universe. This is a problem, as we won't be able to observe it directly. However, luckily for us, these large scales interact with smaller scales, providing us with indirect evidence of this early phase of the universe. One of the effects of these interactions is to create the hemispherical anisotropy. In our current understanding of the universe, the probability that the two hemispheres of the sky would be different is very small. But with loop quantum cosmology corrections, the probability is enhanced, and the observed anisotropy is no longer anomalous. This means that loop quantum cosmology would provide an explanation for anomaly number 3, why the hemispheres in the sky have different average temperatures. In addition, using the model of the universe that loop quantum cosmology provides solves the first two anomalies that we have seen in the cosmic microwave background: strange behavior at large scales and lensing. According to Dr. Parampreet Singh of the National Institute of Technology, Kanpur, this possibility that cosmic microwave background anomalies are not just statistical flukes, but rather effects due to quantum gravity happening very early in the universe is very exciting. But how sure are we that the universe originated in a big bounce? As with all major claims, extraordinary evidence is needed. The idea that the universe originated in the Big Bounce has been suggested several times. We'll have to see if this one sticks. Another problem: our observations are limited, and it may just be that we are observing a part of the universe that is unusual. That's a problem called cosmic variance. As Dr. Don Hajnaki, a co-author of the paper and professor at Penn State University, said, "It is hard to confirm with 100% confidence. Cosmic variance poses a challenge. But what is intriguing is that including these new possibilities can resolve two issues at the same time: the large-scale power suppression and small-scale lensing amplitude. Ruling out signs of a loop quantum cosmology-driven cosmic bounce in Planck data means the cosmic microwave background anomalies remain unexplained.